Hi all. This presentation is about a survey done on LLMs, therefore how effective LLMs are for code generation. So first, we'll start with foundational techniques, which includes the neural architectures like transformers that powers today LLMs. Then we will explore some of the biggest challenges, things like ensuring code correctness, handling long context, dealing with data quality, and addressing security concerns. And after that, we'll walk through the current evaluation landscape and how we are testing these models and why that might not be enough and more rigorous testing is required. And of course, we'll look at the exciting applications which are already in use, like GitHub Copilot, automated testing, and other educational tools. But beyond the tech, we are also going to talk about something even more important, the human side shift of this. LLMs are an interesting thing in this AI field. So, whether you're building tools with LLMs, evaluating them, or just trying to understand how responsibly to integrate them into your workflow, this presentation helps you a bit. So, moving on to large language models are not just improving how we write code, they are fundamentally changing how we think about programming itself. These models are capable of generating code from natural language, therefore, completing partially written code, even detecting bugs, all with a fluency that would seem like an interesting thing. So, moving on. So, the code generation has come a long way. We started with rule based systems, templates, useful, but they are kind of rigid. LLMs mark a true paradigm shift powered by deep learning and massive code. So these models can understand natural language prompts and generate coherent context-aware code. This isn't just a productivity boost, but it's a fundamental change in how we interact with code. LLMs can assist with debugging, documentation, and more, but building these models require massive resources. So while potentially it's important to democratize the existing development and access control remains a key challenges. The pace of change in this field is really interesting. New models, training techniques, and applications are emerging constantly. So it looks at four major pillars: the four core techniques, architecture, and the most pressing challenges, and also the current evaluation methodologies and benchmarks, and how LLMs are applied across software engineering. Finally, we'll discuss future research directions and social impacts. So let's discuss about core techniques. At the core of most code focused LLM is the transformer architecture. It's powerful because it models sequential data like code very effectively. Basically, transformers use self attention to weigh the importance of each token, multi head attention to capture multiple types of relationships in parallel, and they use positional encodings to understand token order. So this allows them to understand variables, functions, and structure in a flexible, scalable way. So the end result is going to be like the models that can write code, complete functions, and reason across different parts of a file. So, but how they are configured matters, which brings us to our next slide. So, transformers based code models come in three flavors: encoder, decoder models like E5 are great for translating NLP to code, they for natural language to code. Decoder only models such as GPT, Codex, and StarCoder are excellent at completing code and handling prompts. And encoder only models like BERT are more about understanding code than generating it. Think tasks like summarization, search, and vulnerability detection. Each architecture serves different use case. Therefore, understanding these distinctions helps when choosing or designing models. In the next slide, we'll take a look at some specific LLMs developed for the code and how they compare in practice. So let's talk about LLMs. So the OpenAI's Codex is a GPT family model trained on public GitHub code. It parts GitHub Copilot and it is good at completion and natural language to code tasks. Then there is AlphaCode from Google DeepMind, which is really good at solving competitive programming challenges using a encoder decoder setup. And also the Salesforce Code T5 and CodeGen is an encoder decoder for multitask use, while CodeGen is a decoder only and it's focused on synthesis. And whereas the star coder from the big code is an open source and trained on permissively licensed code. So this model highlight the diverse design choices shaping the field. So we also have models like prominent code specific LLMs, which are optimized for multilingual code generation, and GPT-4, which is multimodal and which excels at reasoning. What sets these models apart is it's a mix of architecture, training data, composition, and intended application. Some focus on multi-language support, other emphasis on competitive programming or natural language understanding. With new models frequently pushing the boundaries of performance, so to keeping up with the differences in training objectives, data licensing, and model capabilities is crucial for building or evaluating these systems. So training data and methods are just as critical as model architecture. Most generative code models use next token prediction. This teaches them syntax structure and pattern. Others like BERT-based models use masked language modeling to predict hidden tokens, helping with understanding tasks like bug detection. So basically, these models rely on large-scale code, like billions of lines, which are taken from GitHub public repos, often spanning dozens of languages. But the size and quality of this data affect how models behave. So there are three main fine-tuning strategies. Therefore, instruction fine-tuning teaches models to align with user intent through paid prompt code examples. Domain-specific fine-tuning makes model more effective in specialized areas like web domain or blockchain. So prompt engineering and in-context learning are really useful. By carefully designing prompts and even including examples, we can guide LLMs towards more accurate code. Chain of thought prompting, for instance, helps models reason step by step before outputting final code. Then there is retrieval augmented generation or RAG. It fetches relevant documentation, code snippets, or project context before generation, improving accuracy and reducing hallucination. These techniques are especially useful for tailoring LLMs to real world use. Think enterprise APIs or internal libraries. So, the better the context, the better the output. Beyond prompts, there is also reinforcement learning. So, RLHF, that's a human feedback, uses preferences to shape models' behavior, whereas the RLCF does the same but uses signals from the compiler or test results, like whether the code passes or compiles. So, together, these techniques help refine LLM output for usability and correctness. Some teams also combine LLMs with symbolic program synthesis. The LLM drafts code and a formal system checks or it completes it. This hybrid approach could bring us closer to correct code, probably to the correct code, but not just a plausible code. These ideas are transforming how developers and LLMs collaborate. So, a huge challenge for LLMs is semantic correctness. The code they generate might compile, but does it actually do what it's supposed to do? Often, quite not. Models can misuse APIs, apply the wrong algorithm, or miss subtle edge cases. They're great at mimicking the patterns, but coming to deep reasoning, they still struggle. Another issue is hallucination. When models invent functions or libraries that don't exist, it's convincing but dangerous. For real world use case, especially in production, correctness isn't just an optional thing. It's really important and it's critical. So ensuring code logic aligns with the prompt's intent remains an active and vital development area. So as LLMs generate more complex code, verifying it becomes exponentially harder. We might be brilliant at looking function, but under the layers, it could have subtle bugs or misbehaviors. That complexity makes human review more time consuming and error prone. So the initial productivity gains from using LLMs can sometimes be cancelled out by the cost of debugging and validation, but it's not going to take a lot of developer efforts to write code from scratch. So better ways for LLMs to explain their reasoning, offer traceable steps, or even co-generate unit test cases. So transformers are powerful, but context is still a bottleneck. Most models have limit tokens around 4,000 tokens, or maybe 8,000, or maybe some cutting edge models have maybe 100K tokens. But coming to real code base, which spans thousands of files and interdependencies, LLMs often struggle to stay consistent with variables or logic defined far earlier in a file or in a totally different file. Therefore, sparse attention, external memory, and recurrence are being researched to tackle this. Until then, LLMs may function really good within the token size context limits. So, even with terabytes of code online, data quality is a problem. Many programming languages like COBOL or domain specific DSLs are barely represented. So that means LLMs perform poorly in this area. Similarly, highly specialized domains like embedded systems or financial modeling may lack public training data. As a result, LLM which are trained on general purpose code often struggle with um, these kind of use cases. And even in mainstream languages, the quality varies. Bugs, bad patterns, and outdated libraries all exist in the wild, and LLMs learn from them. So, more data isn't always better, and it's clean, curated, and up to date. So, low quality training data creates ripple effects. If a model sees insecure or buggy code often enough, it might start reproducing those same patterns. It could amplify bias. For example, always suggesting certain libraries or style over others just because they are more common in the dataset. This isn't just technical, it's kind of ethical too. It affects accessibility, fairness, and inclusivity. So cleaning up massive code datasets is harder and time consuming, but it's kind of necessary. So researchers and developers are exploring filtering, deduplication, debiasing, and even synthetic data generation. So the goal in general is to more diversify and secure and balance the training sets for future models. Moving on to security vulnerabilities in generated code. One of the most urgent concerns is security. LLMs don't inherently understand secure coding practices. They just replicate what they have seen. So if they have seen insecure code, uh, honestly, there is lots of code in the GitHub open repos. They will reproduce those same vulnerabilities. We're talking about SQL injections, buffer overflows, hard-coded credentials, even though GitHub doesn't allow, but still in other platforms it's possible. Some users intentionally prompts LLM to write malicious code and they succeed. LLMs can generate working malware if asked the right way. This dual use dilemma means developers need to be vigilant and researchers need to build guardrails, checks, and secure by design training protocols. The problem isn't just copying bad code, it's combining harmless pattern into dangerous ones. So LLMs can't always foresee that a certain combination of inputs might introduce a vulnerability. And filtering all insecure examples from training data, basically it's kind of difficult. So we need models that understand what secure code looks like, not just statistically but conceptually. That means incorporating secure coding standards, compiler warnings, and even static analysis into training or fine tuning. So LLMs are kind of magic boxes, honestly. They generate code, but we often don't know why they make certain choices. That's a big issue. If the output is wrong, how do we fix it? There's no visible reasoning chain to follow. Also, the code might be convoluted or use um uncommon idioms that make debugging harder. Developers want to control things like coding style, performance constraints, or naming conventions. But LLMs aren't always good at obeying detailed instructions. Sometimes they miss on few key things in our given prompts or instructions. So we need to be more transparent about the models, therefore better prompting tools and interactive workflows where developers can guide and shape the output more precisely without missing uh, key things or the small components which are essential in the code. So training and running codes focused LLMs is expensive. So we need um, hundreds of GPU, terabytes of training, terabytes of training data, and weeks of compute time. That puts development mostly in the hands of well-funded research labs. Inference is also costly. Long prompts and large models means slower, more expensive completions. This impacts user experience in real-time tools like IDE plugins. So developers and engineers and researchers are exploring model compression, quantization, and hardware accelerators. Basically, the goal is to bring these capabilities to edge-like devices and mobile devices, etc. There are a few societal stakes here, like will LLMs gonna replace the junior devs? Will students learn bad habits from the generated code? And who owns code generated from the scraped open source repository? These questions don't have simple answers. So LLMs could lower the barrier to entry, but they could also deepen inequality if only well-funded organizations can afford the best models. They might save time, but lead to de-skilling if developers stop thinking critically. And bias is also another issue. from overrepresented language to biased data. Ethical, legal, and educational frameworks are essential as we integrate LLMs deeper into the development life cycle. So, measuring LLM's output is tricky. Many use BLEU or ROG, which compare generated text to reference reference answers. Using n-gram overlap, this work okay in natural language, but in code, not so much. Two correct functions can look totally different but do the same thing. Edit distance is another option. How many changes to go from generated code to correct one? So slightly better, but still syntax focused. Code BLEU is a newer metric that combines syntax trees and data flows for more accurate comparisons. But even it's not perfect, functional correctness is still a kind of gold standard here. So, do we really know if the code works? That's where the pass at the rate k comes in. The model generates multiple samples, like maybe 10, maybe something like 100 sometimes. And if at least one passes a test suit, it passes. It's a practical metric used by OpenAI's human evaluation and others. But it heavily depends on the quality of those test cases. Poor tests may lead to misleading results, and generating 100 completions can be compute heavy. Still, pass at the rate k is currently one of the best automated measures we have for functional accuracy. It's a solid starting point, but not the full picture. So let's look at some key benchmarks. HumanEval is a small but high quality set of 164 Python problems, which are kind of handpicked, handwritten with unit tests. And most basic Python problems, MBPP has about 1,000 similar tasks, whereas the automated programming progress standard has a larger and harder data set with real competitive programming problems, whereas the code context is similar, also focused on algorithm skill. Then there is multiple E, which translates these tasks into other languages like Java, C++, and JavaScript. Finally, task-specific benchmarks exist for translations like transcoder, bug fixing like defects.j, and summarization. Together, these provide diverse testing grounds, though most focus on Python for now. So the problem with many benchmarks is they focus almost entirely on functional correctness. Did the code pass the test? But what if it's inefficient? What if it's unreadable or even insecure? So pass at the rate K doesn't capture any of that. Other aspects like style, maintainability, and resource usage aren't well measured yet. Plus, we are missing good metrics for more subjective tasks like summarization or refactoring. And sometimes models pass tests but fail in real world edge cases. So current metrics give us a partial insight, but they miss the full picture of the complete code quality and the design pattern which they have used in generating the code. So we need more holistic evaluations. So there is also a risk of Goodhart's law. When a benchmark becomes the goal, it stops being a good measure. Models can overfit to human eval or MBPP. Learning dataset quirks instead of generalizable skills. So they might ace benchmarks but fail in real development environments. Also, current metrics don't assess how well LLMs meet non-functional requirements like efficiency, modularity, or best practices. That's why human review is still critical. We need new benchmarks and tools that test not just what the code does, but how well it aligns with the uh, broader goals like security, readability of the code, and long term maintainability. So automated tests are really good. Basically, they are fast and cheap, but human evaluation is still the gold standard for judging real code quality. Developers can assess readability, logic structure, idiomatic usage, and whether the solution actually fits the task. They can spot flaws even if the code passes test, but it's expensive, subjective, and hard to scale. That's why researchers basically use rubrics, Likert scales, and peer review systems to standardize human feedback. The best approach combines both which uses both automated metrics for scale and human insights for depth. So this hybrid strategy is essential for enterprise grade code generation and in production environments. So LLMs are already changing how engineers work. Tools like GitHub Copilot and Amazon Code Whisper offer code completion that's far more intelligent than autocomplete. The syntaxes can generate entire functions or classes based on comments or partial code. They understand context and can recommend the right APIs. Other LLMs turn natural language into code, like think SQL queries or data scripts from user prompts. Some models help with bug detection and fixing, therefore flagging the issues or even suggesting patches, and others summarize or document the code, which helps new team members understand complex legacy systems faster. So LLMs can also generate test cases, a huge time saver when aiming for solid coverage. Then can refactor the messy code for better readability or optimize it for performance. Language translation is another emerging use case. Converting Python to JavaScript or even migrating COBOL to modern stacks. In education, LLMs act as tutors, explaining errors, suggesting fixes, and generating examples. Other creative uses include UI code generation from mockups and infrastructure as code templates from natural language. The variety of use cases continues to expand with each model release. So, despite their power, LLMs aren't replacing developers anytime soon. They're assisting them. The current model is augmentation, not complete automation. So, think of them as co pilots. They suggest, but you have to steer them in the right direction that keeps human in control for verification, judgment, and accountability of that code when pushing to the production environment or into the real time. So what's exciting is how interaction data like which suggestions you accept or reject can feed back into the training loop. So that's how the tools like Copilot improve over time to your specific style as well. But this also raises privacy and intellectual property questions. So building these feedback loops ethically and transparently is the key. It's a delicate but powerful dynamic between humans and the machines or LLMs to get better at code generation. So one major research goal is enhancing reasoning. Today, LLMs are great pattern matchers but struggle with multi-step logic and novel problem solving. Integrating formal methods or symbolic logic might change that. Another focus is interpretability and control, helping developers understand why a model load a certain piece of code or letting them enforce specific requirements like style or performance. We also want models to generate more trustworthy code, maybe even provide correctness proof or formal specifications. Combining the creativity of LLMs with the rigor of program synthesis could lead to code that's both flexible and verifiably correct. So the future of LLMs for code isn't just smarter models; it's more about the adaptable ones. Multimodal LLMs will handle images, diagrams, mockups, natural language together, and so on. Imagine like writing front-end code just by uploading a Figma design. Lifelong learning is another big goal, enabling models to continuously learn from new tools, frameworks, and APIs without forgetting the older context, without losing the context. So, an LLM that understands your code base, your team's naming convention, and the particular tech stack and evolves alongside your project, these adaptive personalized agents could redefine what productivity looks like in software development. So security can't be an afterthought. Future models should be trained with secure coding principles baked in. That means recognizing common vulnerability patterns and avoiding them by default. We use also need to use defenses against adversarial prompts, malicious users trying to trick models into generating exploits. On the data side, cleaning and filtering mass uh, code remains a challenge. We'll likely see more use of synthetic data, either to augment low resource language or create tailored training scenarios. Carefully curated and generated generation of the data will help models learn better, safer, and faster, while avoiding legal and ethical minefields around licensing. So, to make LLMs truly useful, we need better human AI collaboration workflows. That means interfaces where devs can guide, correct, and shape outputs, not just receive them. We also need to understand how working with LLMs affects learning, cognitive load, and teamwork. On the ethical side, we need clearer frameworks around bias, fairness, and attribution. Who owns the code? Who is liable if it fails? What happens to the jobs? Education will be key, upskilling the workforce to prompt, critique, and collaborate with these tools. So, in conclusions, LLMs are already reshaping software engineering from auto completion to bug detection. They are embedded in modern workflows. They are powered by transformers trained on massive code bases and fine tuned with increasingly clever techniques. But limitations remain like correctness, security evaluation, and compute costs still need to be worked on, still need to be more efficient. Thank you.